Hi everyone, our topic for today is about integration of rational functions by partial fractions. So for this lesson, you should be able to differentiate improper and proper rational functions, decompose rational functions as sum of partial fractions, and evaluate integrals of rational function by partial fractions. So to learn more about this topic, let us hear from Ma'am Raquel Chodoro, the step-by-step procedure of evaluating integrals of rational functions by partial fractions.
We are going to consider the integrand, which is in rational form, okay, in the form p of x over q of x, where p of x, of course, is the numerator and q of x is the denominator. Okay, and suppose that p of x over q of x is a proper rational function. Now, when we mean proper rational function, it means that the degree of the numerator is less than the degree of the denominator. Therefore, we can decompose the proper rational function into sum of partial fraction. And we are going to classify the rational function, no, into two classification. Okay, first, when the denominator contains linear factors, whether distinct linear factor or repeated linear factor in the form ax plus b. And the other classification is when the denominator contains quadratic factor in the form ax squared plus bx plus c, whether it is distinct or repeated. Okay, and in the discussion, we are going to divide it into two parts. No? The first part of which is when we decompose proper rational function, no, into some of partial fractions where the denominator contains distinct or repeated linear factor. And the second part will be on the discussion of integration of rational function, no, into sum of partial fraction, okay, where the denominator contains quadratic factor ax squared plus bx plus c, which can be either unique or repeated. Okay, so after decomposing fraction, okay, the integrand, no, which is a proper rational function into sum of partial fraction, we can easily integrate, okay, the resulting partial fraction, okay, by uh, maybe it can lead to logarithm, or if it is repeated, no, it may be integrable, okay, by power formula of integration. Okay, so let us have now the discussion on integration of rational function by partial fraction where the denominator q of x are linear. Okay, it may be repeated or unique. Now, the rule is for each factor of the form ax plus b raised to m of the partial fraction, of the rational function, rather, p of x over q of x, it can be decomposed into sum of partial fractions a sub 1 over ax plus b plus a sub 2 over ax plus b raised to the second power plus until we have a sub n over ax plus b raised to m, where a1, a2 up to a sub n are constants to be determined. Now, but in case that if m is equal to 1, no, then only the first term in the sum appears. So meaning the rule is for every distinct linear factor in the form ax plus b, there corresponds linear Okay, there corresponds partial fraction of the form a over ax plus b. This is for distinct linear factor. But if the linear factor is repeated, then we have to follow this rule. Okay? So if the linear factor is distinct, then we will have only the first term. And to illustrate integration of rational functions by partial fraction, where the denominator contains linear factors, no, we will be discussing the examples given here in the lecture notes, but we will do it in the whiteboard. Okay. So for example number one, we are going to consider to evaluate the integral of quantity ax minus 1 times the differential of x over, okay, the denominator is 2x squared minus 3x minus 2. Okay, of course, we can factor the denominator. Although the denominator is quadratic, we have 2x squared minus 3x minus 2. It can be factored as two linear factors. And please take note that the integrand 8x rather minus 1 over 2x squared minus 3x minus 2 is a proper rational function. So we can decompose it into sum of partial fraction. Okay, so um, let us have the decomposition here. Okay, we will consider 8x minus 1 over uh, the denominator 2x squared minus 3x minus 2. And since the denominator can be factored into two linear factors, no, we have 8x minus 1 over the denominator can be factored as 2x, okay, the other factor will have x here. Since negative 3 ang middle term, then this must be negative 2 and this must be positive 1. Okay, so to check, 2x times x will give us 2x squared. Negative 4x plus x will give us negative 3x, and 1 times negative 2 is negative 2. So 8x minus 1 over 2x squared minus 3x minus 2 is equivalently 8x minus 1 over 2x plus 1 x minus 2. Okay, and you can see here that we have two distinct linear factor in the denominator. And according to the rule, for every distinct linear factor in the denominator, there corresponds a partial fraction rather in the form a over the quadratic factor. So hence, if we have 8x minus 1 over, okay, quantity 2x plus 1, x minus 2, okay, now for the linear factor 2x plus 1, there corresponds a over 2x plus 1. There corresponds a partial fraction in the form a over 2x plus 1. And for the linear factor x minus 2, there corresponds a partial fraction in the form b over x minus 2. Okay, so instead of using A1, A2, okay, we will just use A and B for the constant. And A and B here are constants to be determined. So hence, 8x minus 1 over 2x plus 1, x minus 2 can be decomposed into sum of partial fractions a over 2x plus 1 plus b over x minus 2. And To determine the values of A and B, we can actually simplify the resulting equation, no, by multiplying both sides of the equation by the LCD, 2x minus 1 x minus 2. Okay, sorry, this should be 2x plus 1. 2x plus 1 x minus 2. And multiplying the left member by the LCD, 2x plus 1 x minus 2 will give us x minus 1. Okay, and this is equal to a over 2x plus 1 times the LCD will give us a times x minus 2, and the second term times the LCD will give us b times 2x plus 1. So our problem here is how to determine the values of the constants a and b. And we can do that by substituting the values of x that will make the denominator 0. Okay, actually this is a technique, no? Okay, we will use the values of x that will make the denominator 0 to determine the constants a and b. And there are actually two values of x that makes the denominator 0. These are x is equal to 2 and x equals negative 1 half. No? Okay, so if we will use the value x is equal to 2, that is by equating the factor x minus 2 to 0. Okay, if we will substitute x is equal to 2 in the simplified form, okay, 8x minus 1 is equal to a times the quantity x minus 2 plus b times the quantity 2x plus 1. When x is 2, of course, x minus 2 will be 0, right? Okay, so what will happen? We will have 8 times 2 minus 1 is equal to, okay, the right side, in the right side of the equation, the first term will be 0 since 2 minus 2 is 0. Okay, so times is equal to b rather, okay, times the quantity 2 times 2 is 4 plus 1. Okay, so this will give us um, 16 minus 1 is 15, right? Is equal to 5b. And if we will solve for b, then b is equal to 15 over 5, which will give us 3. Okay, so we were able to get the first constant, which is equal to 3. Now, there is another value of x that makes the denominator 0. Okay, and that is x equals negative 1 half. So when x is equal to negative 1 half, okay, by the way, x is equal to negative 1 half is determined by equating 2x plus 1 to 0. When 2x plus 1 is equal to 0, then 2x equals negative 1, so that x equals negative 1 half. And when x is equal to negative 1 half, then the equation becomes 8 times 1 half. Okay, we are going to substitute x equals negative 1 half. Okay, sorry, this must be negative 1 half in this equation. So, okay, let me repeat this. So 8 times negative 1 half, okay, minus 1 is equal to, okay, this time the second term will be 0. So since 2 times negative 1 half will give us negative 1 plus 1. Okay, so in the first term, we will have a times the quantity negative 1 half. Okay, we replace x by negative 1 half minus 2. Okay, now in the left member, a times negative 1 half will give us negative 4 minus 1 is equal to a times, okay, we have negative 1 half minus 4. Negative 1 half minus 4 will give us negative 5 over 2, right? So negative 5 over 2. If we will simplify or combine negative 1 half and minus 2. Okay, so the common denominator is 2, so that gives us negative 1, negative 4, which is equal to negative 5. So the left member is negative 5, okay, and this is equal to negative 5 over 2 times a. And if we will solve for a, then we can just multiply both sides of the equation by uh, negative 2 over 5, okay? Or we can just have this as a is equal to, okay, 2 times 5 will give us 10, no? 10 over 5, so that a is equal to 2. Okay, so we have a is equal to 2 and b is equal to 3. Okay, hence, now we can now say that uh, 8x minus 1 over 2x plus 1, x minus 2 can be decomposed into sum of partial fractions a over 2x plus 1, but since a is equal to 2, then we have 2 over 2x plus 1, okay? Then b is 3, okay? So plus 3 over x minus 2, okay? Did you get it? So this is how we decompose the given integrand 8x minus 1 over 2x squared minus 3x minus 2 into sum of partial fraction. And if we will go back to our problem, no, if we will evaluate the integral of 8x minus 1 over 2x squared minus 3x minus 2, then we can write this as the integral of, okay, after decomposing the rational function, now it gives us 2 over 2x plus 1, okay, plus 3 over x minus 2 times the differential of x. And we can write this as sum of integrals, okay? We can write 2 before the integral sign, right? Okay, so we will have, okay, wait. Let us just not write 2 before the integral sign since the numerator, oh, okay, wait. Let me just write this as the integral of 2 times the differential of x over 2x plus 1, okay, then plus the integral of 3 times the differential of x over x minus 2. Okay, now look at the two integrals. If we are going to evaluate the integrals, no, both leads to logarithm. Okay, now in the first integral, you can see that the numerator is the exact differential of the denominator. Okay, if u is 2x plus 1, the differential of u is 2 dx. Hence, we can use the formula that the integral of the differential of u over u, when the numerator is the exact differential of the denominator, it leads to the natural logarithm of the denominator, right? Okay, therefore, we will have integral of 2 dx over 2x plus 1 is natural logarithm of the denominator 2x plus 1, okay? Then plus, okay, now please take note that the second integral also leads to natural logarithm. The differential of the denominator x minus 2 is equal to the differential of x. Therefore, 3 times the integral of dx over x minus 2 leads to the natural logarithm of ln of x minus 2, then plus the constant of integration. Now, we can also simplify this by using laws of logarithm. Okay, now look here. Okay, in the second natural logarithm, second term, we can use the third law of logarithm. Okay, uh, we have natural logarithm of 2x plus 1, okay, plus natural logarithm of, we can express this as the absolute value of x minus 2 raised to the third power, okay, plus the constant of integration. Okay, got it? Okay, therefore, we will have natural logarithm of, okay, if we will simplify this, then this will give us a natural logarithm of, okay, quantity 2x plus 1, quantity x minus 2 raised to the third power plus the constant of integration. Okay? So we were able to evaluate the integral of quantity 8x minus 1 times the differential of x over 2x squared minus 3x minus 2. Okay, so this is the first example.
So in summary, we have learned that if the degree of the numerator is greater than the degree of the denominator, the fraction is said to be improper. So in such cases, it is first necessary to carry out long division before you proceed to integration. And to evaluate integrals involving proper fractions, the integrand should be expressed first as a sum of partial fractions.